So, we usually think about artificial intelligence operating with this expectation of absolute fluidity.
Right, like it's pure magic.
Exactly, pure magic. I mean, you sit down at your keyboard, you type a prompt, you ask some complex architectural question, and boom.
Yeah, it just appears.
Right. A perfectly structured essay or a highly optimized piece of software just materializes on your screen in seconds.
It feels completely frictionless.
Hmm.
I mean, we've basically been conditioned to interact with this disembodied intelligence that just lives up in the cloud,
Unbothered by the physical world.
completely unbothered by the constraints of physical reality. Yeah,
And that frictionless experience is exactly what we are going to tear apart today in this deep dive.
because it really doesn't hold up, does it?
It doesn't, because when you take that exact same genius level AI and you ask it to do something physical,
Something real.
yeah, something as seemingly basic as just turning on a single tiny little LED light on a raw circuit board, that magic completely falls apart.
It really does. You're looking at a situation where the smartest software in the world is essentially reduced to, well, a confused toddler just banging its head against a wall.
Because you are slamming the instant gratification of cloud computing straight into the unforgiving, messy electrical reality of hardware physics.
Right, because software can deal in abstracts. Hardware, it demands voltage, current, and absolute perfect timing.
Which brings us to our mission for this deep dive. I mean, for you listening, we have a fascinating stack of sources to go through today.
Really incredible stuff.
Yeah, we're looking at raw bench notes, technical embedded engineering logs, and deep dive articles documenting a very specific experiment from August 13th, 2026.
The documentation from that day is just incredible because it captures this massive paradigm shift in real time.
It really does. And I want to set the scene for you based on these notes. So it's a shed in New South Wales, Australia.
A literal shift.
A literal shed. And in this shed, there is a 72-year-old electronics technician sitting at a workbench.
Classic setup.
Right. We're talking about a workspace smelling of solder flux, completely covered in jumper wires and oscilloscopes.
The real deal.
And on this bench, an AI sends this bizarrely simple message over a physical debug wire to a microchip.
And it was just a few characters, right?
Literally just 5 characters. It sends 1, 2 plus dot.
So the number 1, a space, the number 2, a plus sign, and a period.
Exactly. And a fraction of a second later, that 72-year-old technician watches the number 3 appear on his screen.
It gives me goosebumps just thinking about it because the sheer unprecedented nature of that interaction is what we really need to unpack today.
Because it wasn't normal.
No, not at all. We are not talking about an AI writing some C code on a PC
Yeah.
and then, a human copying and pasting that code, compiling it, and running it later.
Right, which is how it usually works.
Exactly. But the logs show a direct, live conversational exchange between a modern AI and a physical microcontroller sitting on a bench.
And that had never happened before in exactly that way.
Never. The AI was literally talking directly to the bare silicon.
So today, we are going to explore why getting an AI to simply add 1 and 2 on a piece of physical hardware was such a massive fundamental breakthrough.
Because it really was.
And to do that, we have to look at why the traditional industry standard way of writing code completely breaks an AI's brain, when it comes to hardware development.
We also really need to dig into the source materials revelation about how this ancient programming language from 1970 suddenly became the ultimate tool for modern artificial intelligence.
Yeah, that part blew my mind. And we're going to explore why physical, tactile, manual bench time with a human being is the absolute only way to teach an AI true hardware intuition.
It's mandatory.
It is. So whether you write Python or JavaScript for a living, or even if you are a seasoned embedded developer who knows your way around a breadboard, this deep dive is going to fundamentally change how you think about the speed of feedback loops.
And the limitations of modern AI, frankly.
Absolutely. So to understand the victory of that moment in the Australian shed, we first have to understand the massive systemic failure that preceded it, right?
Right. And our sources point directly to a process called the C loop as the primary obstacle preventing AI from mastering hardware.
So let's lay out exactly what this C loop is, because, to a lot of developers listening, it's just the water they swim in.
Yeah, it's just standard operating procedure.
Right. So why is it the villain of our story?
Well, the C loop is the traditional embedded development cycle. It is the way hardware development has been done for decades, obviously heavily reliant on the C programming language.
Sure.
And to understand why it's so punishing for an AI, We need to break down the mechanics of what actually happens when you want to change one tiny thing on a microchip.
Okay, let's walk through it.
Let's say you want to change a pin from a low voltage to a high voltage.
Okay.
First, you write some code in C on your host computer.
Okay, step one, write the code. That part is straightforward.
But then you have to compile it. And compiling isn't just a simple translation. I mean, it's a whole ordeal.
Right, there are layers to it.
Exactly. First, your computer has to run a preprocessor to handle macros and includes.
So pulling in all the external files and definitions.
Yeah, exactly.
Yeah.
And then the compiler kicks in and translates your C code into assembly language.
Okay.
Then an assembler converts that assembly into raw machine code, the actual ones and zeros.
And we're still not done.
Not even close.
Yeah.
Then a linker takes all your different files and all those precompiled libraries and stitches them together.
Right, and it has to assign physical memory addresses to every single variable and function, right?
Precisely. And all of this is happening on your big, powerful desktop PC.
So at this point, all that work has happened, and the code still isn't even on the chip itself.
No, not at all. You just have a binary file sitting on your hard drive.
Right.
Next, you have to stop the debugger, which is the hardware tool that acts as your bridge to the actual chip.
Okay, stop the debugger.
Then you have to send a command to physically erase the flash memory on the microcontroller.
And that takes time.
It takes actual time because it involves applying a specific electrical voltage to clear the memory cells.
Right, it's a physical electrical process. It's not just a software deletion where you just hit backspace.
Exactly. You are physically wiping the slate clean, and once the memory is wiped clean, you write or flash that new binary file onto the chip over a serial cable or a USB interface.
And flashing takes time too.
But yeah, it takes time just to push the data and then to verify that every single byte arrived correctly.
Wow.
And then finally, you restart the debugger, you issue a command to reset the chip's CPU, the chip boots up, it runs all its initialization routines, and then it finally executes your new program.
And only at that point can you observe the outcome to see if your tiny little voltage change actually worked.
Exactly.
So if I'm a developer sitting at my desk, how long does that entire dance take, from the moment I hit save to the moment I see the result?
I mean, depending on the complexity of the project and the speed of your interface, each cycle can take 30 seconds, a minute, or sometimes much longer if you're dealing with a massive code base.
Right. And if you are listening to this and you build software, a 1-minute compile time probably sounds like a coffee break to you.
Yeah, it's nothing for a human.
Right. You
Sure.
hit build, you check your phone, maybe take a sip of coffee, and you look back at the screen. It is perfectly normal. So why is this perfectly normal industry standard loop utterly devastating for an AI?
Well, the reason really comes down to the architecture of how an AI thinks, specifically regarding its context window.
Okay, break that down for me.
Humans have a working memory that can, idly wander. We can get distracted by a text message, and then we snap back to the problem at hand with all the relevant context still intact in our heads.
Right, we remember what we were trying to achieve before we checked our phone.
Exactly. But an AI does not have that kind of persistent dialogical memory.
It doesn't have a hippocampus storing away the grand strategy.
No, it operates strictly as a context machine. Large language models function by holding a highly fragile, immediate mental model of the current task within their token buffer.
Within the token buffer, right.
Yeah. Every time you interact with it, it is essentially recalculating its next move based entirely on the prompt you just fed it, plus its immediate short-term history.
So its thought process is highly immediate.
Very immediate. It's thinking, I am trying to achieve this goal, I just changed variable X, therefore I expect outcome Y, and I received outcome Z.
And it holds all those variables in this really delicate balance.
Right. And when you force the AI to sit there and wait a full minute in silence for the C loop to finish compiling, erasing, flashing, and rebooting,
The context just completely shatters.
it shatters. Every single round trip through that C loop breaks the AI's attention mechanism.
Because the feedback is simply too slow.
Way too slow. And our sources use a brilliant analogy for this. They compare it to driving a rover on Mars.
Oh, I really want to dig into that analogy because it perfectly visualizes the mechanical problem here for you listening.
Yeah, so imagine you are an operator sitting in a control room here on Earth.
Okay.
And you're using a joystick to control a robotic rover on the surface of Mars. You have a camera feed showing you what the rover sees.
Sounds fun so far.
Right. But the critical issue is the speed of light. The radio signal takes roughly 14 minutes to travel through the vacuum of space from Earth to Mars.
And another 14 minutes for the camera feed to actually get back to you.
Exactly. So you're always seeing what the rover was doing 14 minutes ago in the past.
Which is terrifying if you're driving it.
Totally. So you're watching the screen, and suddenly you see the rover heading straight toward a massive crater.
Oh no!
You immediately pull back on the joystick and hit the stop button.
And here's a catch. The stop command is going to take 14 minutes to traverse the vacuum of space.
Exactly. By the time that command actually arrives in the rover's receiver on Mars, the rover has already driven off the cliff and smashed into pieces at the bottom of the crater.
Because for those entire 14 minutes, the physical machine just kept acting on old instructions.
Right. The feedback loop between your action hitting stop and the rover's reality was fundamentally disconnected by latency.
So, taking that Mars rover analogy a step further and applying it to our AI trying to program a microchip, the C loop is the vacuum of space.
That is the absolute perfect way to frame it. The C loop is the vacuum of space.
Because by the time the C loop finishes its massive sequence of compiling, linking, erasing, flashing, and running,
By the time the physical electrical result of the AI's code change finally comes back over the wire.
the AI's hypothesis has gone entirely stale.
Yes. It cannot hold that fragile thread of logic across a minute-long delay. The AI essentially forgets what it was trying to prove by the time the proof actually arrives.
It really feels like trying to play speed chess via the postal service.
Well, that's a good way to put it.
Right. I mean, you can be an absolute grandmaster of the game. You can see 20 moves ahead on the board. But if you are forced to wait 3 days between every single move, you completely lose the thread of your strategy.
You lose the rhythm entirely.
Yeah. By the time the letter arrives in the mail with your opponent's counter move, you're staring at the board thinking, wait, why did I move my knight to that square last week? What was my plan?
The latency destroys the strategy.
The latency destroys the strategy entirely. And our sources actually document the real-world consequences of this postal service chess game.
Yeah, they really do. Before this successful breakthrough in the shed, a previous iteration of the AI attempted to perform some relatively basic hardware tasks using this traditional C loop.
What were they trying to build in that earlier attempt?
The goal was to get a small LCD screen initialized and displaying text, along with an NFC reader.
Like the radio frequency chip you use when you tap your credit card to pay for something?
Exactly the same kind of chip. And in the grand scheme of embedded engineering, these are standard, well-documented tasks.
Right, there are libraries for that.
Tons of them.
Mm-hmm.
But the AI floundered completely.
When you say it floundered, does that mean the AI was just generating hallucinations? Like, was it just writing bad C code?
See, that is the most tragic part of the logs. The AI's code was technically excellent.
Really?
Yeah, it can write boilerplate C code in its sleep. It understands the syntax perfectly. It understands the libraries.
So why did it fail?
It failed because it lost its mental edge. Every single time, it had to sit in silence and wait for the chip to flash.
Ah, the context window collapse.
Exactly. It would generate a brilliant hypothesis, write the code, the human would hit compile, they would wait a minute, the screen would stay blank, and by the time they fed that failure back into the prompt, the context was gone.
So it would just start guessing.
Yeah, the AI would start chasing its own tail. It would suggest fixes for problems that didn't exist or would revert changes it had just successfully made.
Because the C loop is a context killer.
A complete context killer. The logs note that they spent a whole day doing this. They burned through massive amounts of API computing credits, generating thousands and thousands of tokens. And at the end of the day, almost nothing worked.
Wow.
The AI wasn't failing at embedded development because it lacked coding skills. It was failing because the development environment itself was intrinsically hostile to how a large language model maintains its train of thought.
Okay, so we have established our primary constraint. If the latency of the C loop, the literal minutes of waiting for a host PC to compile and flash memory, is destroying the AI's context,
Right.
then the only viable solution is finding a way to collapse minutes into milliseconds. We have to eliminate the delay entirely.
We'll have to close the gap.
Which brings us to the tool they used in the shed. We really need to talk about Forth.
Yes. The resurgence of Forth in this specific context is one of the most fascinating technical pivots in the documentation.
It really is.
We're specifically talking about a modern variant called macrystallurus Forth.
Now, I have to play devil's advocate here for a second.
Go for it.
Forth was invented in the early 1970s. It is literally older than the internet.
True.
If Forth is so instantaneous and brilliant, why did the entire software industry abandon it for C in the first place? I mean, why are we dragging a 50-year-old language out of the graveyard if it's supposed to be the key to our hyper-advanced AI future?
That's a really fair question. The industry moved to C because C is incredibly good at abstraction.
Okay, abstraction.
Yeah, and building massive, complex operating systems.
Hmm.
C allows human teams to work together on millions of lines of code without stepping on each other's toes.
Because it hides the complex hardware details from the programmer.
Exactly. But Forth is entirely different. Forth is incredibly close to the bare metal. It relies on a concept called stack discipline.
Stacked discipline. What does that mean in practice?
Specifically, it uses a last and first out data stack, which
Hmm.
can be very difficult for human programmers to keep straight in their heads as a program grows large.
Okay, explain what you mean by a last and first out stack.
Think of a stack of plates at a buffet.
Okay, plates at a buffet. I'm with you.
When you add a clean plate, you put it on the top of the stack. When someone takes a plate, they take it off the top.
Right. You never pull a plate from the bottom or the whole thing crashes.
Exactly. Forth works the exact same way with computer memory. If you want to add the numbers 1 and 2, you don't write 1 plus 2 like you would in normal math or in C.
Right.
Instead, you write 1, 2 plus XC.
Ooh, reverse Polish notation, like those old Hewlett-Packard calculators?
Yes, exactly. Reverse Polish notation. Mechanically, you push the number 1 onto the top of the stack.
Okay,
Then you push the number 2 onto the top of the stack right above the 1.
got it.
Then you call the plus operator. And the plus operator is designed to automatically pull the top 2 numbers off the stack.
So it grabs the 2 and the 1?
Right. It routes them through the chip's arithmetic logic unit, adds them together, and then pushes the resulting 3 back onto the top of the stack.
Okay, so that's what the AI typed in the shed.
Yeah.
1, 2 plus dot.
Yes. And the dot command simply takes whatever is currently on the top of the stack, which is now the 3, and prints it to the screen.
Okay, so the syntax is definitely weird for anyone used to modern languages, but how does that solve our latency problem? How does that bypass the massive delay of the C loop?
It solves it because of how Forth handles compilation.
Okay, how so?
Well, in the C loop, we discussed how you need a massive desktop PC to run the compiler, the assembler, and the linker.
Right, because a C compiler like GCC is huge.
It's millions of lines of code. It requires gigabytes of RAM to run. But the Metcrisp Stellaris Forth compiler is incredibly tiny.
Oh, tiny.
We're talking just a few kilobytes. It is so small that it does not live on your PC at all. The compiler lives on the silicon chip itself.
Wait, the tiny microchip, the one that barely has enough memory to run a basic program, that chip is doing the translating.
Yes, it is a technical marvel. There's absolutely no compiling happening on the PC.
None.
None. There's no flashing process initiated by a desktop tool. There's no stopping the debugger to apply voltage to erase pages of memory.
Whoa. The entire environment, the compiler, the runtime, the interpreter, is fully self-contained inside the microcontroller's own memory.
So what mechanically happens when the AI types a command into the terminal?
When the AI types a word, which is what Forth calls a command into the terminal, that raw text is sent straight down the wire to the chip.
Okay.
And the chip's internal Forth system reads that text, instantly compiles it into native machine code directly in its own memory, and executes it.
Immediately.
Immediately, in a matter of microseconds.
So it's not a batch process where you write 1,000 lines of code, bundle it up, and send it over the wall to see if it works.
No, it is fully interactive.
Yeah.
It utilizes what computer scientists call a REPL.
Right, a read, evil, print loop.
Exactly. You type something, the chip reads it, evaluates it, executes it, and prints the result back to you instantly.
And this brings us right back to the 1, 2 plus dot moment from the shed.
Precisely. In the traditional C loop, asking the chip to just add 1 and 2 and show you the result would require writing a boilerplate C program, including standard I/O libraries, setting up a main function,
Compiling it, halting the chip, erasing the flash memory,
writing the new firmware, rebooting the CPU.
initializing the serial port, and finally reading the output.
That's exhausting just to list out.
But with Forth's REPL on the chip, the AI tagged 5 characters, and the hardware responded in microseconds. The feedback loop goes from minutes down to milliseconds.
The impact that must have on the AI's token buffer is just massive. I mean, this instant terminal feedback perfectly aligns with the AI's fragile context window.
It really does.
The Mars rover delay we were talking about completely evaporates.
Right, the signal arrives and the result comes back before the rover can even move a millimeter.
So the AI can actually maintain its train of thought.
Yes, It states, I am changing variable X, and in the literal blink of an eye, the silicon responds, here is outcome Y.
The AI never has the opportunity to forget what hypothesis it was testing.
Exactly. A REPL is essentially the only interface an AI can work inside without suffering context collapse.
It allows the AI to stay in a state of continuous flow.
Flow is the perfect word for it. It is iterating, guessing, testing, and adjusting at the speed of its own thought processing, rather than being bottlenecked by the physical speed of a flash memory eraser.
But, here is a critical nuance documented in the sources that we really need to clarify for you listening.
Yeah, this is important.
You have this 72-year-old technician in the shed sitting next to the AI working through this fourth REPL. And a really common assumption is that the human had to sit there and teach the AI this obscure 1970s syntax from scratch.
Right. You'd think the human is acting as a translator, like, okay, AI, you want to set a variable, here's how you format that in reverse Polish notation.
Yeah, that's what I assumed when I first read it.
But the logs show that wasn't the case at all. The AI already knew Forth natively.
Really?
In fact, it knew it better than most humans alive.
Yeah.
It had ingested every manual, every textbook, every piece of open source Forth code ever published on GitHub or old Usenet forums.
So it already had the grammar down flawlessly.
Flawlessly. It understood the stack discipline perfectly. It could generate highly optimized Forth code faster than any human.
Okay, but if I'm following the logic here, that raises a massive contradiction.
How so?
Well, if the AI already knew the language perfectly, and it finally had this instant fourth REPL feedback loop that protected its context window, why was the human technician there at all?
Yeah.
I mean, why did that guy need to sit in a shed in Australia and teach it if the AI was already a fourth master?
That is the big question. And the answer is because knowing the grammatical syntax of a language is not the same thing as knowing the physical world.
That's a profound distinction. We need to dig into that. What is the actual difference between syntax and physical reality for an AI?
This exposes the core blind spot of modern AI. You have to remember,
Yeah.
an AI is trained entirely on text.
Right. Words on a screen.
Yes. It knows the syntax of Forth because it's read millions of words describing it, but it possesses absolutely zero training data on what it feels like to use Forth connected to raw, unforgiving, embedded hardware.
It has no physical intuition.
None at all.
It's like it knows the theory of how a combustion engine works, but it has no idea what to do when the engine physically floods with gasoline on a cold morning.
That's a great way to put it. The bench logs detail some very specific, highly technical hurdles they ran into that perfectly illustrate this lack of physical awareness.
Give me an example.
Okay, let's look at the fourth command, compile a flash.
Okay, what does that command do?
In Microsoft Solaris Forth, the system usually runs in RAM. Now, RAM is fast, but it's volatile.
Meaning if you lose power, the code is gone forever.
Exactly. So compile to flash tells the system to switch its dictionary pointer over to the permanent flash memory. So the code you write next is saved permanently.
Makes sense.
And the AI understood the command, but it had no intuition for the physical architecture of the memory map.
What do you mean?
If that command accidentally targets the wrong dictionary space in the chip's physical flash memory, it overwrites the compiler itself.
Oh, wow. It essentially lobotomizes the chip by writing over its own brain.
Yes. The AI would confidently execute the command, not realizing the physical memory alignment was wrong, and suddenly the chip would just die.
Because it erased the very thing that let it speak.
Exactly. So the human technician had to step in and explain the physical memory boundaries.
Wow.
Another great example from the logs involves a command called bis.
This bit set.
Yes, bit set. It is used to set a specific bit in a hardware register to a 1.
Okay.
The AI knew the command existed, but it lacked the engineering intuition that this specific physical hardware required a bit mask rather than just the raw decimal number of the bit's position.
Okay, let's pause and break down what a bit mask is for anyone who hasn't dug into binary math recently.
Sure. A hardware register is basically a row of 32 physical switches inside the silicon.
Okay, 32 switches in a row.
Right. Let's say you want to flip the 5th switch to on.
Okay.
If you just send the decimal number 5 to the register, well, the number 5 in binary is 0101. So you aren't just flipping the 5th switch. You are accidentally flipping the 1st and 3rd switches and turning everything else off.
Because it just overwrites the whole row of switches with that new 0101 pattern, rather than just targeting the one single switch you actually care about.
Exactly. You wreck the whole register. To target just the 5th switch, you need a bit mask.
How does that work?
You take a binary 1 and you logically shift it over 5 positions. This creates a pattern that is all zeros, except for a 1 in the 5th spot.
Got it.
Then you apply that mask using a logical OR operation. That safely flips only that one switch.
But the AI didn't know to do that.
No, the AI kept trying to just write raw numbers, causing the hardware to behave erratically.
Yeah.
The syntax was valid for it, but the physical application was disastrous.
It's fascinating because these are nuances of the physical silicon that aren't always documented clearly in the textbooks the AI was trained on.
Exactly.
It's tribal knowledge. You only get it from actually burning up components on a bench.
And the most glaring example of this disconnect was how the AI handled write-only registers.
Write-only registers. Okay.
Yeah, in embedded hardware, some memory locations are physically designed as one-way streets.
Meaning?
You can send data to them to control a peripheral, but the physical wiring does not allow you to read data back from them. The silicon pathways simply don't exist in that direction.
But the AI doesn't know that.
No. The AI, acting as a purely logical software entity, tried to perform a standard read-modify-write operation.
Okay, so it wanted to change one setting.
Right, so it tried to read the register's current state, change the specific bit it cared about, and write the whole package back.
But because it is a write-only register, what happens when it tries to read it?
The read operation returns garbage, or sometimes it returns all zeros, or triggers a hardware fault.
Oh, boy.
So the AI reads garbage, modifies the garbage, and writes the garbage back.
And the hardware just goes completely haywire.
Yes. And the AI is completely baffled because, syntactically, its read-modify-write code is flawless.
But it lacked the physical intuition that this specific memory address on this specific piece of silicon is a one-way street.
Exactly.
You know, we usually operate under this assumption that AI is going to arrive and automate human engineers out of a job. We always think of it replacing human intervention.
Right, the AI takes over everything.
Yeah. But looking at these bench logs, the tactile, dirty, manual bench time is the exact missing ingredient required to fill the gap in the AI's intuition. It is a true partnership.
It really is. The bench session documented in these 2026 logs is collaborative development in its absolute purest form.
Two highly specialized entities covering each other's weaknesses.
Precisely. The AI brought the processing speed, the flawless grammatical syntax, the ability to generate boilerplate code, and pull reference manual data instantly.
And the human brought 40 years of knowing what silicon registers actually do when you apply voltage to them.
40 years of burned fingers, blown capacitors, and tactile hardware intuition.
So how did they actually facilitate this collaboration physically? I mean, were they just sitting at a desk, passing a keyboard back and forth, like, my turn, your turn?
Oh, no. The technical setup was much more elegant than just sharing a keyboard.
How'd they do it?
The logs show they used a debugger daemon. It's a background software program running on a little Raspberry Pi connected to the chip.
Okay.
And that allowed up to 8 clients to share a single fourth kernel simultaneously.
Meaning the human's laptop and the AI server were both logged into the exact same chip at the exact same time.
Yes, using a terminal multiplexer. The human and the AI worked in the exact same terminal window, talking to the exact same piece of silicon at the same time.
It was a shared live workspace.
Exactly. The human would steer the high-level strategy and provide the physical intuition, and the AI would instantly suggest the specific fourth words and calculate those tricky bit masks.
And the chip would answer both of them instantly via the REPL.
Right. When the AI sent a command to probe a memory address, the human watched the hexadecimal answer appear live on his own screen.
That is incredible. They are literally finishing each other's sentences in machine code.
It's beautiful, honestly.
But let me pause there, because I want to play devil's advocate again.
Go ahead.
Having instant feedback from the chip via Forth is fantastic, and having a human mentor to guide the AI's physical intuition is crucial.
Absolutely.
But in the world of hardware, just because the CPU instantly prints OK to the terminal doesn't necessarily mean the physical world actually complied with your request, right?
That is such a good point, and it raises one of the most important concepts in embedded engineering. It's a trap that almost all software developers fall into when they first move to hardware.
Which is?
In embedded systems, instant does not mean correct.
Because software can lie.
Software can absolutely lie.
Give me an example of how that happens.
Well, the CPU might execute your code perfectly, evaluate the logic, and report back as success code to the terminal. But what if the physical pin on the outside of the chip has been burned out by a short circuit?
Oh, right. The software wouldn't know that.
Exactly. Or what if there's a hardware conflict in the bus matrix? What if a clock signal isn't running? How do you actually know the physical silicon is doing what the software code says it's doing?
You can't just trust the CPU's word for
You
it.
cannot trust the CPU. You need an independent referee.
An independent referee.
Yes, you need a way to look at the hardware that completely bypasses the software.
And according to the logs, this is where a tool called Regmon enters the narrative.
Regmon, which stands for Register Monitor, is the independent referee for hardware state verification. It is the tool that forces the software to tell the truth.
Okay, what does that actually mean in practice? How does it act as a referee?
It reads the chip's internal hardware registers, the literal physical switches inside the silicon that control everything from pins to timers, and it reads them live, completely independent of the CPU running the fourth code.
Wait, I want to understand the mechanics of that. If the CPU is the brain of the chip and the CPU controls the memory, how can Regmon look at the registers without asking the CPU to fetch that information for it?
Because of a fundamental hardware design concept called independent debug paths.
Okay.
This is crucial to understanding the reliability of this setup. Modern microcontrollers have dedicated debug hardware built directly into the silicon,
Oh, okay.
often using protocols like SWD, which stands for Serial Wire Debug, or JTAG.
So there are literal physical pins on the chip dedicated solely to debugging.
Yes, and inside the chip, that debug port connects to a debug access port that has its own direct connection to the memory bus.
Bypassing the CPU.
It bypasses the processing core entirely. The debug interface is a completely separate hardware pathway from the CPU that is busy running the fourth REPL.
It's like having a backdoor camera installed directly into a bank vault.
That is a brilliant analogy. They read the exact same memory addresses, but they do it through entirely independent physical paths.
So Regmon can't be fooled by a software bug.
Regmon cannot be fooled by software logic errors. It cannot be fooled by a crashed CPU in an infinite loop. It cannot be fooled by a flawed fourth compiler.
It just looks at the raw reality.
It looks directly at the hardware states via the boundary scan cells and the debug bus. It acts as the ultimate, unfoolable truth.
To build on that bank vault analogy, it's exactly like having an independent financial auditor counting the physical stacks of cash in the vault, rather than just asking the bank manager what the Excel spreadsheet says.
Exactly.
Because the spreadsheet, the software might say you have $1 million. The CPU says the transaction was successful, but the auditor opens the physical vault door, looks inside, and says, nope, the shelves are empty, the money isn't here.
Regmon is the auditor.
And the bench logs provide a beautiful deep dive example of this exact dynamic playing out, don't they?
They do. Let's walk through the very first physical hardware task the human and the AI tried to accomplish together. Turning on a single green LED on the circuit board.
Turning on a green light. On the surface, that sounds like the simplest thing in the world.
The AI approached it logically. It evaluated the schematic, generated the correct fourth word to apply voltage to the pin connected to the green LED, and sent the command through the REPL.
And what was the result?
Nothing happened. The LED stayed completely dark.
Did the software throw an error?
No. The fourth REPL reported success.
Of course it did.
It evaluated the command, executed the machine code, and returned to the prompt ready for the next command. The software said the vault was full, but the physical world said otherwise.
So instead of having the AI blindly guess what went wrong and rewrite the code 50 times, they consulted the referee.
They looked at Regmon, and Regmon, reading through that independent SWD debug path, revealed the physical truth. A specific hardware register called GPIOC motor was reading a 0.
GPIOC motor. That sounds incredibly cryptic. What does that register physically control?
Let's break it down. GPIO stands for General Purpose Input-Output.
Okay.
The C means it's a specific block of pins grouped together as port C.
Right.
And motor stands for Mode Register. This register controls whether the physical pins on port C are acting as inputs, meaning they are listening for electrical signals coming in from the outside world, or outputs, meaning they are actively driving electrical current out to the board.
And Regmon showed that this mode register was reading all zeros.
Because it was reading 0, it meant that every single physical pin on port C was configured in its default state, which is as an input.
Oh, I see where this is going. An LED requires current to turn on. It needs an output.
Exactly. You can write software commands to an output data latch all day long.
Right.
The CPU will happily execute those instructions.
Right.
But if the physical pin on the edge of the chip is configured in a high impedance state to listen as an input rather than push-pull mode to speak as an output, it physically cannot drive electrical current to an LED.
The electrons will not flow.
The electrons will not flow.
But why was the pin set as an input in the first place? Didn't the AI tell it to be an output?
The AI assumed the hardware was already initialized. It assumed an operating system or a bootloader had already done the dirty work of setting up the port modes.
But on bare metal, there is no operating system.
Exactly. The setup routine that tells the silicon to make that pin an output had never actually been run. The AI assumed the hardware was ready. The physical reality was that it was not.
So how did they bridge that gap? How did they fix it using Redmon?
The human technician guided the AI to write a specific fourth command to manually set the specific bit for that pin GPIOC motor 9 to output mode.
Okay.
And the moment they executed that command, the logs described something beautiful happening on the technician's screen. Regmon's text display for that specific register literally flashed yellow.
Wait, Redmon provides a visual diff of the hardware states?
Yes. The terminal interface for Regmon highlights any register that changes state since the last pull.
That's incredibly useful.
It is. The yellow flash confirmed, via the independent debug cable, that the physical state of the silicon had actually undeniably changed from input to output.
And I'm guessing.
And the literal millisecond that register flashed yellow on the screen. The green LED on the board lit up.
The auditor confirmed the cache was in the vault, and the physical world matched the software intent.
Exactly. They didn't take the AI's word for it. They didn't even take the fourth compiler's word for it. They read the actual register via an independent hardware path.
That's just brilliant.
But the logs show they took it one step further to prove the absolute trustworthiness of this tripartite system, the AI, the human, and the referee.
What did they do?
They performed a tactile blind test.
Oh, this is where the physical reality of the bench really shines. Walk me through the blind test.
So the human technician configured a different pin on the chip to act as a pull-up input.
What does pull-up mean in this context?
It means an internal resistor inside the chip is physically connecting that pin to the power supply. So by default, if nothing is connected to the outside of the pin, it reads as a high voltage, which the software interprets as a binary 1.
Okay, so the pin naturally floats high at a 1. Got it.
Then, using his actual physical fingers, the technician took a jumper wire.
Like just a piece of copper wire.
Exactly. He plugged one end into the ground rail of the circuit board, and he manually touched the other end to the pull-up input pin, physically shorting it to ground.
So he is physically forcing the electrical signal down to 0 volts.
He physically forced it to 0. And the AI, constantly pulling that pin through its fourth software loop, instantly reported to the terminal that it was seeing a 0.
So the software successfully observed the physical change the human made.
Yes. But again, in embedded systems, we don't just trust the software.
Right.
So they immediately looked at Regmon, and Regmon, reading through the independent SWD debug port, entirely bypassing the CPU, also confirmed that the input data register for that pin had changed to 0.
2 completely independent hardware paths yielding one identical answer.
2 paths, 1 answer. That is the definition of a trustworthy embedded system.
Because you have the blistering processing speed of the AI generating the software logic, and you have the absolute certainty of the hardware monitor verifying the physical reality.
Exactly.
You know, getting a green LED to turn on, I want to contextualize this for you listening. Because to an outsider, or maybe a web developer who just works with HTML, turning on a single light bulb sounds incredibly trivial.
It sounds like nothing.
Right. But in the hardware engineering world, this represents crossing a massive threshold, doesn't it?
Oh, it is the ultimate threshold. In the embedded world, getting an LED to turn on and off under your control is universally known as the blinky rite of passage.
Blinky.
Yes. It is the hello world of hardware, but vastly more complicated to achieve.
Why is it so much more complicated? I mean, hello world on a PC just requires a print statement. It takes 2 seconds.
Because to print hello world on a PC, you are relying on millions of lines of operating system code to handle the graphics card, the monitor, the memory management. You don't have to think about any of it.
Right. All the heavy lifting is done for you.
But when you are working close to the bare metal, getting that LED to blink proves that the entire fundamental tool chain is functional.
Because if even one tiny link in that chain is broken, the light stays dark.
Exactly. If the blinky works, it proves several massive concepts simultaneously.
What does it prove?
It proves your compiler is successfully generating valid machine code for that specific ARM architecture.
Okay.
It proves your upload mechanism is successfully moving those bits over the wire and writing them to the correct physical memory addresses.
Right.
It proves the chip's internal CPU clock is running at the correct speed to execute the code. And it proves your independent observation tools, like Regmon, are correctly showing you the result.
It is the definitive proof of life for the system.
The expert documenting the session in our source material highlighted a profound philosophy regarding this moment.
What was it?
Once you, or in this case, an AI partner, can reliably turn an LED on and off by manipulating hardware registers with Forth, you have kicked open the door.
You have dominion over the physical silicon.
Yes. Everything you attempt after that moment, whether it's configuring a complex I2C bus to read an NFC card, driving a stepper motor for a robotic arm, or weeding gyro sensors to fly a drone.
It's all built on that foundation.
It is all just more words. The fundamental barrier between software abstraction and physical physics has been breached.
Wow. Let's pull back and synthesize what we've uncovered here today. When we look back at that scene in the shed, the AI sending commands over a wire, the 72-year-old technician providing decades of physical intuition, the instant REPL feedback, and the Blinky coming to life. What is the real narrative here?
The real story is absolutely not simply that an AI was taught to write in the Forth programming language.
Because that's too simple.
Right. If that is the takeaway, we miss the point entirely. The fundamental breakthrough is that an AI finally found a physical development loop fast enough to keep its fragile context window intact.
It defeated the C loop. It solved the Mars rover latency delay.
It bypassed the delay entirely. It turned out that Forth, this hyper-efficient bare metal language from 1970 that the modern tech industry had largely written off as a historical curiosity, was sitting there all along.
It was just waiting for an intelligence that could finally use its instant self-hosting compilation to its maximum potential.
Exactly. The AI didn't need to be taught the grammatical syntax of Forth. It needed to be shown the bench.
It needed the tactile physical intuition of a human mentor.
And the unfoolable truth of Reijman's independent debug paths to anchor its rapid-fire software intelligence to physical electrical reality.
It completely reframes how we need to think about creating reliable embedded systems in the age of artificial intelligence. I mean, it wasn't the AI doing it alone in the cloud, hallucinating C code.
Right.
And it wasn't the human doing it alone with a soldering iron and a data sheet.
No, it was this incredible tight-knit symphony. The AI's massive data processing speed, the human's manual bench intuition, the instant feedback of the on-chip Forth RAPL, and the independent referee of Regmon verifying the physics.
All working in absolute simultaneous concert.
It serves as a literal blueprint for the future of hardware development.
It really does.
The workflow becomes a conversation. You type a word, you watch the silicon react physically, you check the independent register monitor to ensure the reaction was real, you iterate and move on.
And the entire cycle happens in milliseconds.
Zero context is lost. The AI stays perfectly sharp, and the hardware is forced to stay honest.
As we wrap up this deep dive, let's trace the journey we've taken through these sources. We started with the fatal flaw of the traditional C loop, how its minute-long compilation and flashing latency completely destroys an AI's token-based context window, rendering it unable to maintain a strategy.
We examined how the elegant resurrection of a 1970s architecture, specifically Makecrisp's Stellaris Forth, solved that latency by moving the entire compiler directly onto the silicon itself, providing the instant REPL feedback an AI desperately requires to function.
We unpacked the absolute necessity of manual, physical bench work, how an AI might have memorized every textbook and datasheet in the world, but it still fundamentally requires a human mentor to teach it the raw, tactile intuition of hardware.
The realities of write-only registers, bit masks, and floating pins.
Right. And finally, we explored the critical role of Regmon, the independent, unfoolable referee that leverages separate physical hardware debug paths, like SWD, to verify that the silicon is actually doing what the software claims it's doing.
Protecting the system from software lies.
Which leaves us with a really fascinating, provocative thought to mull over as we close this out. If an AI's greatest limitation in mastering physical hardware is simply the latency of its feedback loop, what other obsolete bare metal tools from the past might be the hidden keys to unlocking AI's future?
It is a vital question for the industry. I mean, as we try to push artificial intelligence out of the browser and into robotics, into industrial automation, into manufacturing plants, are we looking too far forward?
Are we trying to invent massively complex new software frameworks when the perfect instant feedback solutions are already hiding in the forgotten, dusty manuals of the 1970s?
Exactly.
It makes you wonder what other ancient, highly optimized tools are just waiting in a shed somewhere, ready to be paired with a modern neural network, Because as we saw in the logs today, the magic of software only becomes real when it respects the physics of hardware. The philosopher eventually has to learn how to turn the wrench.
And the documentation proves they cannot learn to turn that wrench alone.
Uh-huh.
They need the bench.
So to borrow the cryptic sign-off wisdom written directly into the logs from that brilliant bench session in New South Wales, don't be like Og. Get out there, find a bench, and always check your independent registers. Thank you so much for taking this deep dive with us.